Let us create dynamical behaviors for all the components of servo system involved in the movement of the system. We will first start with the mechanism modeling. For obtaining the mechanism there are two basic options. One is automatic translation from mechanism representation to model for Kodyard-Daimola behavior modeling. The other one is creating the model by hand using Kodyard-Daimola behavior modeling libraries. In this case, 3D Experience translates automatically the mechanism representation into a Modelica model. It takes into account the geometric information, assembly information, degrees of freedom, materials, weights, inertial momentums, etc. Result is a Modelica model which can be used in RFLP app. It is possible to open and edit this model by using Kodyard-Daimola behavior modeling app. In the functional and logical design application, insert existing physical system. Select the logic block. In action bar, select the behaviors menu. Click Insert New Behavior Representation. New content window is open. In this window select Daimola behavior. The new behavior representation is inserted in the selected logical block. Observe the behavior representation link inserted in the logical block. This links the logical block with Kodyard-Daimola behavior modeling. You have now prepared the logical design diagram to allocate the dynamical behavior. Select the desired logical block, click twice the Kodyard-Daimola behavior modeling link. In action bar select Behavior Tools menu. Select Main Model in the package browser tree and click Generate from Kinematic. Go to the tree and select the mechanism representation of the servo system. Select appropriate parent class and output class name. The model is generated. Drag the translated model from the package browser tree and drop it into the 2D graph. We will create a connection. This connects the logical block input to the translated Modelica model that is to Revolute joint of servo system. We can observe all the elements of the model. We can also edit certain parameters by clicking on the individual elements. Let us now model the DC motor and gearbox. We will use following specifications for DC motor and gearbox. There are 4 methods to model simple DC motor and gearbox. We can model the motor by using a high-level DC motor model from the library, using basic and simpler components from the library, using equations, and using block diagrams. We will use the second method to model the DC motor and gearbox. We will search for the components from the Modelica standard library. We will drag and drop the components and then draw the connections as shown. We will introduce the parameters of the components from the motor and gearbox specifications table. Click twice each component to open the parameters window. We will create the following behavior by choosing appropriate blocks from the Modelica standard library. We can check the behavior of the DC motor gearbox model before we introduce it in the whole system. It could be of interest to simulate it. This can be done in the same Kodyard-Daimola behavior modeling window, by adding some extra components. This plot shows the gearbox speed, RPM, for a 12-volt step input signal. You can now introduce the DC motor gearbox model in the whole system by doing the following connection. We will now see the behavior for power electronics block. We have given two behaviors to this block. The objective of the power electronics block is to adapt the voltage to the maximum voltage range of the DC motor, providing enough intensity. Because the power of the selected DC motor is very low, there are several technological possibilities: power operational amplifier, PWM, etc. Here a power operational amplifier working as inverted amplifier with unit gain will be used. Also, it is possible to create a model for the power electronic block by using different techniques. We will use Modelica blocks to model power electronics. For creating the model, search for the components in Modelica library. In the CATIA Dymola behavior modeling diagram view, drag and drop the components. Draw the connections as shown. Introduce the parameters of the components from the motor and gearbox specifications table. We can even simulate power electronics before introducing them to the whole system. Although the main objective of power electronics is to provide enough power to the DC motor, it is also possible to include the inner control loop, the electrical current loop, for the servo system. Next behavior shows a reduced version of the previous controller. The only difference is that here we are using only an integral controller, I, instead of a PI. We can use only an integral, I, controller because in this control loop we are only interested in reducing the steady-state error. Let us see modeling for sensors. In this case, sensors have been included in the DC motor gearbox logical block, although it would have been more convenient to include them in sensors transducers logical block. You can later modify their position in the logical diagram. In the behaviors, you can see that we have used three Modelica sensors: rotational angle sensor, rotational speed sensor, and electrical analog current sensor in the DC motor gearbox model. We have used the sensors transducers logical block just for transforming angular data from radians into degrees. Reference signal behavior have been created by using the kinematics PTP2 block from the library. This source block is capable of creating a point-to-point trajectory from a starting point to an end point by using LSPB, linear segments with parabolic blends, interpolation. In the following pictures you can see the angular position and angular speed profiles created and used as reference signals for the dynamic controller. This figure shows a typical architecture for servo systems. Block having green color is the controller part already built, and red-colored blocks are to be built in this stage. This feedback control system has three control loops: current loop, inner, it controls the motor current and, therefore, the DC motor torque. This control loop has already been developed and included in the power electronics behavior model. We have developed a proportional integral controller, PI, and an integral controller, I. We will use the integral controller in this case. Speed loop, it controls the rotational speed of the mechanism. In our case we want to develop a proportional integral controller, PI. Also, because we want to control the joint's maximum acceleration, a speed reference signal with an adequate speed profile is needed. This will be part of the signal to follow for this control loop. This controller will also receive the actual speed signal in the position controller output. Position loop, outer, it controls mechanism angular position. In this case just a proportional controller, P, will be used. It needs the desired position reference signal and, of course, the actual mechanism position. This control architecture can be very easily created in CATIA Dymola behavior modeling app by using blocks from Modelica library. Just drag and drop the blocks. Connect and edit the blocks as indicated in the figure. We will now add context behavior to root logic block. Once we have created the logical diagram, the necessary behaviors and the physical system, requirements and functional diagram are not necessary in this step. We can simulate the mechatronic servo system. Here simulation means, to obtain the time-varying dynamic behavior, movement, of the servo system for a specific input signal. This is useful for tuning the dynamic controller's parameters and also for checking the behavior of the full mechatronic system before connecting it to the real mechanical set. For starting the simulation of the full developed system, it is necessary to insert both the logical diagram and the physical product into the CATIA Functional and Logical Design app. In the Functional and Logical Design app, you can select, in the tree or in the 2D graph, logical block for choosing its behavior, or you can choose the root logical node for choosing behavior for all the logical blocks. In Action Bar, select Behaviors menu. Select Behavior Selection. The Behavior Selection window opens. In this window you can see 3 columns: logical blocks, dynamics behaviors and context behaviors. If more than one behavior is available for a logical block, you will see a downward arrow. For choosing the desired behavior, click the arrow and select the adequate model. Once all the desired behaviors are selected in the Behavior Selection window, press OK to validate the selection. You can proceed to simulate the system. Insert logical diagram and the physical product into the CATIA Functional and Logical Design app. Select Behaviors for all logical blocks. In the Action Bar, select Behaviors menu. Click Execution Setup. Execution Setup window opens. Configure the following elements: in General tab, Start Time and Stop Time. In Integration tab, Output Interval and Integration. The setup depends on your system. For our servo system, the following parameters work properly. Click OK. Select the root logical node in the tree. In the Action Bar, select Behaviors menu. Click Simulate. Then Translation and Model Compilation starts. When translation is done, a new window, with all the logical blocks and their parameters and variables can be seen. This window is mainly used for selecting variables to plot. Experience Player window opens after translation. There are several options and indicators to control the simulation. Press play to start the simulation. For leaving the simulation environment, press Simulate button in the Behaviors menu. With early virtual behavior simulation and validation during the design phase, engineers are able to anticipate actual results of design in various conditions. This facilitates better control over planning and cost.